Um, I know this is not a title that in agenda I kind of change it in the last minutes because something wrong with my results. So today I'm gonna present part of my results here. My name is Wenqi. I'm from School of Natural Resource, PhD student, and my advisor is Dr. Yi. And today I'm gonna talk about quantifying temporal anomalies in normalized agricultural water status. So let's go for the basic questions, my research motivations. Like as the state missions in Water for Food institution, we are all looking for a way to increase agricultural sustainability, which is really critical to monitoring the water stress because drought has really done some damage to our agricultural system. That's why my really general long-term goal is gonna be translate our cutting edge open source remote sensing to improve the actual agricultural water management. However, right now the knowledge gap, I think, is the way that we determine the water stress levels mainly relies on the variations of any vegetation indices, whichever can be sensed by remote sensing technology. Just for example, to put it in a simple way, like we have ET like decrease 1% from yesterday, then people will considering that was the water stress. So right now, I think there's a knowledge gap because we didn't really validate this assumption by actually calculating the standardized anomaly to extreme environment. That's why here's the objective. I have 3 simple objectives here. I'm gonna actually first I'm gonna examine the current remote sensing technology in estimate vegetation water content, and then develop a standard anomaly in vegetation water content under stress environmental with respect to the long-term records. And lastly, will be investigate the correlation between vegetation water content and some other environmental-based drought indicators. Okay, so here is my study sites. That site is the map in the lab is the geographical location near me. It's a tiny city in Nebraska, and we have 2 sites. One is irrigated, and another is rain-fed for the comparison purpose. This site also belongs to the Amir Flux and Nebraska Eastern Research Extension Center. So I'm lucky to have the data that collects since 2003. This is our all ground data. I calculate the leaf water vegetation content, which really simple, just leaf water mass divided by leaf area. And another one is the canopy water content. That was just leaf water content multiplied leaf area index. It's really easy to calculate. So here is the methodology flow. I don't want to bore you in the detail. So in the left box was the whole part of remote sensing estimation. And I used the ASD spectrometer to estimate leaf water content. And I got pretty good result in the summer. And then for the satellite image, I chose Sentinel-2 and Landsat-8 because they have a really historical long-term record. So I use that also can estimate canopy water, vegetation water content. Those whole boxes is done with a lot of estimation with a huge amount of data points. So to be simplified, the result is that I can prove that some really traditional vegetation water spectral index like NDWI, NDII, GVNI, MSI, those are all can be really effective to characterize the temporal availability of the canopy vegetation water content. I've done some like validations and correlation analysis. So because canopy water content really have a good results, I intend to calculate its standard seasonal trends with polynomial regression model. This is the part that so the picture on the right, the green dot was the seasonal distributions of canopy water content, starting from day 0, which is the day they emergence, and to the harvesting day, which is the day they die. The green dots showing that they have a really high variability, and the black line was the seasonal trends. I consider that was the baseline for the normal vegetation water content. So the next step is to convert that to standardized anomaly. So I calculate a really simple concept called z-score, which is the relative difference between each green dots to the black line. And also we call it residual in statistical term. So that would be standardized to a value between negative 0.05 to 2. So negative value will absolutely indicate the stress level, which also means how far it was to the normal value. So those standardized normal value would be correlated with two really famous drought indicator. One of the USDN drought classification, and the one is standard precipitation index. I correlate those two, but unluckily, vegetation water content doesn't really show any difference in drought year and normal year according to USDN. And I cannot find any correlations between vegetation water content standard anomalies to SPI through week 1 to 12. I know this is kind of like really not really happy results, but my outcome summaries, even though the vegetation water content doesn't prove to be that effective, I still think this approach that using the standardized anomaly can give some additional information to actually apply any vegetation indicators to water management, to agricultural water management, because it manifests the change through time. Yeah, that's it. So thank you.